Let us see another technique of general analysis techniques. When we say general analysis technique, we call it as general analysis techniques. They are basically three things. One is KVL, KCL, mesh and nodal, mesh here, and tie set and cut set. All are basically same. The only difference is number of variables. Okay. This is for 1 and 2 variables. This is for 2 and 3, 4 and above. Here we directly calculate branch currents and also branch voltages. Whereas here we calculate loop currents, node voltages, like that. From then we will calculate branch currents, branch voltages. Here we calculate tie set current, cut set voltage. From that we will calculate branch current and branch voltages. Please remember, ultimately we calculate branch currents and branch voltages. But do we calculate directly? It's called KVL, KCL. If you calculate loop currents and or nodal currents, then you come for branch currents and branch voltages. We call it as mesh and nodal. If you are calculating tie set currents or cut set voltages, by using them you calculate branch currents and branch voltages. We call it as what you call tie set and cut set analysis. Therefore, we have these three types of analysis. As I've been telling, I named this as general analysis technique for one reason. The reason is any technique for any circuit. There's no specific thing. It can be applied anywhere. Only the number of variables are different. So this is what we have been doing. In the previous lectures, we studied on this first portion. And now in these lectures, we will be studying on this. Then later, we will go on this portion. So totally, 3 ways to approach circuit analysis techniques. You know why we named as techniques? Because when we go for techniques, we can easily say, without techniques for analysis, we can never do for analysis. So let me take you for what we call mesh analysis. When we say mesh analysis, as I said, they are used for 1 or 2 variables, 2 or 3 variables. You can use for that. It is solved in the form of equations. Why I am saying this is in the form of equations is, this is equations, this is matrix. That's why. Then how many loops are there? How many equations required? Number of equations is equal to number of loops. Number of equations required is number of loops. So what do we do from there? We calculate loop currents. From loop currents, we go for branch currents. each branch has how much current we can calculate. Similarly, we calculate branch voltages also. And there is a very important condition or check that is called sigma Vk Ik is equal to 0. What does it mean? That K is equal to 1 to B. B means number of branches. So Vk Ik means the power. The power involved is 0. The power, total power in a circuit is always 0 because we are saying no radiation is possible. The main assumption for the circuit analysis is no radiation, no power is lost, no power is gained. That's why this has to prove this. And this is the basic idea about mesh analysis. So when we go to nodal analysis, we will have in nodal analysis same comparison if we take. This is also for 2 or 3 variables. This is also in equation form. Here also number of equations is equal to number of nodes. But one important precaution here, when you say number of equations, number of nodes, it is definitely one equation less than this. Then what do we do? Suppose these equations are n, mesh equations are n, the number of equations here is n minus 1. Why minus 1? Because the first one of the nodes is taken as a reference. That's why if you have 3 equations here, you will have 2 equations here. You will understand as I take some examples. Then the fourth point is, from the node voltages you get, after calculating node voltages, we will go for branch voltages. And when you go for branch voltages, finally you will end up with branch currents. And therefore, once again you can cross check Vk Ik is equal to 0. So, whether you follow this one or that one, finally, whether you follow this equation or this equation, everywhere the total power consumed in a circuit will be 0. So these are the basic meanings of what we do. This is equations for loops. These are equations for nodes. So with that we will solve for loop equations here, nodal equations there. From there finally every problem you have to go for branch currents, branch voltages, branch voltages, branch currents. This is what general analysis technique is. And now we will be seeing different examples or problems what can be asked in the exam. In mesh analysis, we have super mesh. Second one is in nodal analysis we have super node. What is it basically? When you have a single current source, this is called ideal current source without shunt resistance. Suppose if you have an ideal current source without shunt resistance, the voltage across that we don't know. In such case, we cannot apply ordinary mesh, we should apply super mesh. Similarly, ideal voltage source without series resistance. In such case also, you cannot know the voltage between them or the current between them. So here in this case, voltage is not known. In this case, current is not known. When you don't know the voltage, you can't apply mesh equation. We need to bypass it. That is called super mesh. when you don't know the current equation or current value, you cannot apply node, because in mesh we talk with voltages, voltage is not known. In nodal equation we talk about currents, current is not known. So when current is not known, what you do? You go for super mesh. When voltage is not known, what to do? We go for super mesh here, super node here. These are the two aspects we need to know before we enter into problems. And how many mesh equations required? For example, number of mesh equations required is equal to number of loops minus number of ideal current sources. If you have a number of ideal current sources, you have less number of equations required. Similarly, number of equations required is equal to number of loops, nodes minus number of ideal voltage source. So this is for mesh, this is for nodal. So what is happening? Whenever there is an ideal current source, number of equations required is decreased. When you have an ideal voltage source, number of nodal equations required is also decreased. So when the equations are decreasing, we should really take this approach and solve it faster. So whenever you have ideal voltage sources, don't worry, go for mesh. So normally there is something going on in among students. They have been told, or they have an understanding thinking, whenever current source is there, apply nodal. That's not correct. When the current source is there, best approach is mesh, because the number of equations decreased. When voltage sources are there, the best approach is nodal. So that wrong notion which is prevailing among students, you need to be cross-checked, they need to be avoided. So let's not worry whenever there is a current source. That is really helping us to solve our equations. So this is about how to use the concept of super mesh, super node. So having this small idea, then when we go into problems, we can literally see what is a super mesh and super node. This is an idea to approach our problems. So let us see, for example, suppose I will give a small example. Here is a voltage source, here is a resistor, and suppose you have current, and then like this. Small example. Say this is Y1, R1, R2, R3. This is I1, this is I2. This is independent, so let us say Vs. Say this is something called 2Vx. This 2Vx means what you know? Voltage, control, current source. This voltage is controlling the current source here. Okay. Then, how to apply this? Actually, we need two equations here. Number of equations required is 1 and 2. 2 loops, 2 equations. But luckily, if you see this 2Vx here, this is I1 minus I2 over. One equation is already over. Why I1? I1 is in the same. What is the current in this branch? I1 and I2 both are flowing. Here you have I1, here you have I2, but here it's a difference of those two. So 2Vx is equal to I1 minus I2. And then you cannot apply KVL here because this voltage is not known to you. Why the voltage is not known? Because it's a current source. What current source is it? This current source is without shunt resistance. Suppose if there is a shunt resistance, you can convert it to voltage source and still you can apply KVL. Therefore, when there is a current source, you better don't touch it, and you can't apply KVL because the voltage is not known. Even this you cannot apply again because it's not known. So you cannot apply voltage KVL for this loop or this loop. Mesh equations fail. In such case, we take it as, we call it as KVL to I1, I2. It's not I1 loop or I2 loop, it is combined loop. Because it is more than one loop, our elders named it as super mesh. The super mesh is a word more than one mesh. That's an idea, simple. Whenever we don't know anything extraordinary happen, we call it a super. So similarly, this is also super, more than one. Then how to apply? You go by this way. Plus Vs minus I1 R1 minus R3 I2 is equal to 0 over. This minus this over. We are not coming here. And that's why I named this as relation. This is not an equation, it's a relation. What is the relation? The relation for these two. This we call it an equation, this we don't call an equation. Or you can call it equation, but that's not coming from KVL, that is coming from a relation. 2Vx is equal to I1 minus I2. What happened now? When I need two equations, one equation is reduced. That's why if you apply here, number of mesh equations required is equal to number of loops minus current source. That's why if you apply, how many loops are there? 2. How many current sources are there? 1. How many equations required? 1. That is it. So whenever we have a current source in a loop, number of currents are, number of equations are decreased. Number of equations decrease there. Similarly, even in nodal voltage, number of equations will decrease. So always see, wherever applicable, please go for relation, then go for equation. Try to reduce the number of equations and make it very short. So one important precaution in mesh and nodal analysis. For GATE competitive exams like PSU, public sector units, even in IES objective exam, they cannot ask such a big problems, because solving 3 equations, 2 equations is very difficult. When solving 2 equations, 3 equations is difficult, what to do is, the next option is, they are still asking the questions but not solving. They are simply asking the question by saying, obtain equations. So the objective question exam is asking for equations only. That's a very important precaution. But they know one secret, if equation is right, the problem is right. Solution will automatically come. So they want to check with you whether you know how to apply the equations in more than one loop and more than one loop with current sources, voltage sources. That means super mesh and super node concepts. So this is the basic precaution with which I am going to enter into problems. And as I have explained, both KVL and mesh, KVL and KCL, mesh means nothing but KVL, Kirchhoff's voltage law. Nodal means nothing but KCL. So we will still apply KVL and KCL, but not for a branch wise, it is for a loop wise or a node wise. So if you apply KVL for a branch wise, it is called KVL alone. If you apply KVL for a mesh or loop, it is called mesh. And KCL for nodes, it is called nodal analysis. This is applicable to higher circuits. So let us go and see some problems. Let us see nodal analysis. Nodal analysis is mathematical technique for determination of node voltages. So in each equation we will have nodal voltages. We calculate nodal voltages. From then we calculate nodal branch voltages and branch currents. What is a nodal analysis? It is nothing but KCL and linked with Ohm's law. And what is mesh analysis? That is nothing but KVL linked with Ohm's law. So these are the two equations or two analysis techniques we have. Here also we have super node. As I told you, super node is nothing but whenever there is a voltage source without resistor. What's the current in that? We don't know. When we don't know any current, such a thing we cannot apply. So we will always go for super node. Super means more than one node. So what is the number of equations required? Number of equations required is equal to number of nodes minus number of ideal voltage sources. Ideal voltage source means a voltage source without series resistance. So, these are the basic definitions for our problems to go, and we will see problems. This is an example to see how a super node is connected. For example, when you see this problem, between two nodes we have circled voltage source. That voltage source does not have any resistance along, that is why that is called super node. I will explain in the problems how to take up each super node and handle. Then how to calculate loops there. You have loop 1, loop 2, and this is also to explain how to handle different loops and write the mesh equations possible. As I told you, they will only ask equations. They do not ask you to solve, because writing equations for 2 marks is more than sufficient. Solving will take more than 5 minutes, and most of the competitive exams or objective exams, you do not need to have that. And we can solve a problem either by mesh or by nodal. Both will give same conclusions. There are 2 alternative methods. You do not have any preference to say what to use, but generally we go for nodal, because nodal generally gives one equation less than mesh. So, this is the meaning, and that is how you can always prefer. Like KVL and KCL, most of the problems we solve by KCL. Between mesh and nodal, most of the problems we solve by nodal. But if they say write the mesh equations, we have to write mesh equations only. So, let us go to problems one by one. Look at the problem 1. I am going to solve the problems. The first problem I have taken is basically a simple AC circuit. The first element I have taken is R. Okay. Second element L. Third element is C. These are the 3 elements we have. This is V naught cos omega naught t, for example. This is resistance, for example 1 ohm. This is inductor 1 Henry. This is capacitor, for example 1 farad. The question is, obtain the mesh equations. We call it as I1, we call it as I2. These are the mesh equations. Please remember, these are not, though it is time domain equations, we are solving in frequency domain. V of t, let us call it, is minus R into I1 minus L into di1 by dt into I1 minus I2 is equal to 0. That is the equation you have. And if you really apply frequency domain, it is called V of omega, I1 of omega, j omega L, I1 of omega minus I2 of omega is equal to 0. What exactly I am trying to say is, you are converting time domain into frequency domain. This is actually called time domain. This is actually called frequency domain. And the time domain to frequency domain we have converted into Fourier transform. And similarly, if you go to S domain, you will have V of S here minus R into I1 of S minus Ls into I1 of S minus I2 of S is equal to 0. What exactly I am trying to show you? A time domain equation converted into frequency domain. Frequency domain, again it is converted into S domain. From now onwards, we have a very interesting saying to say, R becomes R, R becomes R, L becomes j omega L, 1 by j omega C, okay, and then the other one is C becomes 1 by j omega C, 1 by LC. This is 1 by, simply speaking, it is Ls, and S is here. So, please understand, from now, whenever I go for AC analysis, either I will be in time domain or in F domain or in S domain. So time domain, frequency domain, or S domain. This is approach you can take. In fact, one day the GATE exam, the question paper was obtain mesh equations in terms of S domain. He gave objectives we always call MCQ, that is multiple choice questions. In that multiple choice, he gave in S domain. You have to, whatever the objective questions they are giving, they may give equation in the form of time domain or in the form of frequency domain or in the form of S domain. From now we will be using this and make it very, very fast. Then let me go for the second equation. This is called KVL2 I1. All this I have done for I1. When I am going for I1, this is I1, I2 is opposing, that's why minus. Let me go to KVL2 I2. That means second loop. When I apply for second loop, what happens is, I am going from here, say, there is no voltage source in the second loop. So 1 by C integral I2 dt, then minus L di2 minus d1 by dt is equal to 0. So simple. There is no source here, 0, minus this, minus this. Now you please apply frequency domain there. 0 is anyway can be neglected, or you can say 1 by j omega c, okay, into I2 half omega minus j omega L into I2 of omega minus I1 of omega is equal to 0. The same thing if I go for S domain, 0 is 0 as it is, 1 by SC I2 of S, that is Ls I2 of S minus I1 of S. Please observe my notations here. The notations are, when I am writing time domain, I am writing small letters. When I am writing frequency domain, I am writing capital letters, because from time domain to frequency domain, we are using a transform. The transform is nothing but Fourier transform. Here, S domain, again I am using capital letters. So, the whole idea of this lecture is how to write the equations. Why? Because solving them is very easy. In fact, if it is a conventional exam like IAS exam, once you get the equation, you solve them. If it is objective, just write the equation, that's more than sufficient. So these are the two things they are asking, right? Write the equations, solving is small job. If the equations are correct, solution will be automatically correct. So these are the two approaches how to get time domain, frequency domain. Every time you don't need to convert into this, into S domain. Most of the time we go for frequency domain. So frequency domain is for sinusoidal, non-sinusoidal. S domain is better. S means Laplace transform. This is Fourier transform. Let me tell you there. So this is Fourier, this is Laplace. That's how we are going to handle this problem. So take one problem and see how to write the equations. This is called first problem to explain how to write mesh equations. We have seen mesh equations for the same problem. I am going to show nodal equations. When you say nodal equations, we need to know how many nodes are there. There are two loops and two nodes. But the advantage of node is you can ground it. When you ground it, we need only one equation. Let me apply KCL. At which node? At VA. That's called. And when you, as I've been telling, you always assume currents are leaving. That means VA minus V of t by R, that's one current. This voltage minus this voltage. Put for example plus minus. Then what's the current in this? C d by dt of VA. What is the current in this? 1 over L integral VA dt is equal to 0. The current in this branch, the current in this branch, and current in this branch, 3 branches. And if you convert into S domain or frequency domain, what happens is VA of omega, V of omega by R plus C into j omega into VA of omega plus 1 over j omega L into VA of omega. So this is how you can convert into omega domain, or as I told you earlier, this is time domain, this is frequency domain. If it is S domain, what happens there? Let us see what happens to S domain. VA becomes VA of S, V of S by R. This is CS into VI of S plus 1 by j omega L into VI of S is equal to 0. So like this, every time you can convert the equation from time domain to frequency domain, time domain to S domain. So I am just introducing this problem. We are not doing any great thing here, not solving it, it's just making you to understand how to write a equation. So by this, you have seen in one problem how to write a mesh equation and how to write a nodal equation. Wantedly, I took all three components to show you. I have taken all three components because what happens to inductor, what happens to capacitor, you must understand, and also what happens to capacitor, inductor, when writing for nodal, you must understand. So this is an illustrative example to really know how to apply mesh and how to apply nodal. With this, we will go to little higher problems. So let us see another problem to understand how to write super mesh in the mesh equations. I am taking an example. For example, this is a voltage source, independent, this is resistance, this is here current source, and then I have these things. This is how the circuit is given. For example, this is R1, R2, R3, R4. These are the four resistances we have. This is 2Vx and this is 3Vy. The moment you see dependent source, you should always seek for in the circuit how this is working. I mean, where is it depending on? This is depending on Vx. That is Vx possible. This is Vy minus plus. So plus minus is Vx, minus plus is Vy. So these are the three equations we have. For example, now you say this is I1, I2, I3. And this problem is second problem for us. In this problem, question is obtain equations for mesh. Obtain equations. Only equations. As I told you at the beginning, we are not going to solve them. We are only going to for the equations there. And when you go for this equation, this is Vs, for example. Please understand, never proceed without knowing, defining the dependent. For example, we need to define Vx here. When we apply the Vx there, what is that? This is R2 into I2. That's a definition. Similarly, you have to apply, you have to define what is Vy. Vy is depending here, that is minus R3 I3. This is across Vx, this is across Vy. So keep these definitions ready first. So look at the dependent sources, observe where they are depending on, and once observing where they are depending on, put the equations and then go for equations they are asking. First thing is, we need to search for, is there any ideal current source? That you please search for. This is a voltage source. Voltage source in a mesh analysis is not a problem. The voltage source, not a problem. This is a current source, is a problem. So whenever there is a current source without any shunt resistance, series resistance there or not is not an issue. Even if there is series resistance, we don't know across this one. That's why whenever there is a current source, you should skip it. How to skip it? Therefore, as I told you already, number of equations required is equal to number of loops minus number of ideal current sources. So how many loops are there now? 3 loops are here. When you have 3 loops minus 1 current source, you need only 2 equations. So whenever there is a current source, you need 2 equations in that. And therefore, first thing you go for relation. That is, I said 3Vy is equal to I1 minus I2. This is not a KVL. This is not a KCL. It's not any equation. So I don't know what to call it. I don't want to name anything. As I said, I have named this as relation. Please remember, whenever equations fail, go for relation. That happens in day-to-day life. Even in our day-to-day life between a boss and an employee, there will be always some equations. There will be a problem between the equations. You should do that, I should do this. When equations fail, there will be a rupture. But if they want to continue in the same, they need to understand the relation. That's why I give a big statement. Whenever there is a problem with equations, go for relation and you can solve it. So solving any issue is basically relations there. So you may forget all these equations, you can't forget my statement, which is useful for throughout your life. So here equation failed because of this source. Why this equation failed? Because the voltage across this current source is not known. And hence, go for relation. Next one is automatically, you can go for KVL. KVL for loop 2. I mean, here is not a problem. Why? This is voltage source, not a problem. This is drop, not a problem. This is drop, not a problem. The problem is only here. Therefore, I am applying KVL there. For example, I'll start here, then say 2Vx plus minus Vx minus R4 into I2 minus I3 is equal to 0. Please understand, some people by mistake they are starting again the writing R2 I2. Don't write it. Once you already define it, always enjoy this. So plus 2Vx minus Vx minus R4 I2 minus I3. Then lastly, we need 3 equations. No, 1 relation, 2 equations. Now where should I write this equation? Can I write a mesh equation here? No. Can I write a mesh equation here? No, because this is hindering us. Can I write an equation from there to here? Again it is hindering us. Thus, wherever you are going through the current source, you cannot understand the voltage, therefore mesh equation fails. Mesh equation failed there. So when the mesh equation fails, as I told you, go for I1, I2, I3. This is called more than one, and hence it is called super mesh. So please go to super mesh, that is more than one. Let me write, please see there. I am starting here, for example. Whenever you talk about loop equations, you should start and end there. So therefore, first go with Vs minus R1 I1, this is the drop here. Come here, minus Vx, come here, plus Vy is equal to 0. Though the word seems to be frightening, the mesh equation really solving it, this became very simpler than the previous. You are going outer and outer. This is the loop that you have. So you are trying to bypass whenever there is a current source. Therefore, whenever there is a current source, go for mesh equations. That is simply to say, skipping the current source. And when what is this current? This current is I1 minus I3. How do you know it is I1 minus I3? Why not I3 minus I1? It all depends on the direction. This is I1, opposing is I2. So this is about second problem to illustrate when there is a current source, how to avoid it.